Hello everyone. In the last couple of videos, we have seen point operations on images. Today we will see local operations on images. So rather than working on a pixel by pixel, we would see how we can work on the nearby pixels and of the image and get some very meaningful information from an image. So convolution is one such operation that we can perform. And convolution can achieve something that the previous methods of manipulating images can't achieve. Some of this is the blurring, sharpening, edge detection, noise reduction. Edge detection is a very important operation in image processing. So even if it is quite old, it is still a very important operation. This is because a human eye, it has the ability to recognize object using different type of edges, and edges arise in image because of several different physical phenomena such as shadow boundaries, change in the material or reflectance, texture, changes to surface normals, and occlusion boundaries. So this is a paper on which edges matter by Ayush Bansal. If you look at this paper, it is it tells you how different type of edges matter differently. So for example, this is the image here. Now, what are the edges that are possible? On the curtain, the edges are from the point of view of an image, the curtain print, okay, this is a edge. So the texture of the material could be the edges. Similarly, any print here, okay, that could be the edges. Depth can create a sense of a edge. The shadow, the shading here, okay, the shading also gives you a feeling of an edge. And the shadow gives another kind of a edge. So these edges are important to determine the objects that we see in the image. So this we will see what the convolution operator is. So what happens in a convolution operation is, suppose you have this image, a 6x6 image, which is normalized image. 0 is the dark and 1 is 255. 255 is white. Suppose you had everything else dark and just this portion is white, and you want to identify the diagonal edges as a filter and vertical edges. So you can apply a mask or a filter or a kernel. Each of them are, these words are used interchangeably. It means the same thing. Generally, the mask or the filter is a 3x3 filter, but if your image is big, you can go with 5x5 or 7x7 if the image is too big. If the image is too small, you can go with a 1x1 filter as well. It will be as good as your pixel. So what happens in a local operation is that this filter is kept on this area, and the center point of your mask, okay, that is changed. So let's see how that change happens. And each filter is trying to detect a small pattern, okay, just in the local neighborhood. So if I keep this filter here, this pattern perfectly matches this filter, okay. So I should get a very nice pattern detector here. So let's see how this convolution operation happens. The filter is, as I told you, is kept here, and you will do a weighted summation, okay, of this matrix with this matrix. And so you will just multiply 1 into 1 is 1, 0 into minus 1 is 0, 0 into minus 1 is 0. Similarly, the other stuff, and you will get 1 plus 1 plus 1, that is 3. So you're going to do a weighted summation of this kernel with your image. Then you would shift this kernel to the right. It is called as a stride. You will shift it by 1 pixel. This convolution operation is the basic operation in convolution neural net, the CNN of deep learning. Okay, you can shift it, it is called a stride. When you shift it with stride is equal to 1, when you shift your filter on by 1 pixel on the your base image, again you would do the weighted sum. Okay, so this would be -1 into 1 -1, everything else is 0, -1 and +1 cancels out, so your answer is -1. So once you finish with the horizontal movement, then on the vertical side you would move again by 1 pixel. Now if your image is big, you can keep the stride as 2. Okay, but currently I'm just showing it with a stride of 1. Now in this case, where we have not given any padding on the image, what happens is this edges, pixels on the edges, they get ignored, and your 6x6 original image, you will get an image which is called a feature map in CNN. You will get a 4x4 image, and in this 4x4 image, if you notice very carefully, wherever this pattern has matched perfectly, there your weighted summation is the maximum. Okay, so this is the convolution operation. Let us look at this operation in Python. You can apply as many filters as you want, and when you apply multiple filters, the resultant matrix that you get is called the feature map. Okay, so I have imported this image called the new image. The image looks like this. This is the image, and there are multiple edges here, right? So what is an edge in this image will be a gradient which should be from gray to black, and then from black to gray back. Okay, and there are a lot of edges here, and you can apply filter to detect this edges. That is the goal here. So you read the image. Now this kernel, what I have given is, I have given the 0 value in the middle, so that there is a gradient in the kernel, that my immediate pixel value here is high, and here it will become low, and then again immediately high. Now this kernel I have just given by myself, but there are well-defined kernels already which are used for edge detection, but you can use your own kernel as well. First we will see with our own kernel, and then we will see the Sobel edge filter. So you can define your kernel. Okay, let's see the shape of the image. This is 95 cross 158. Now what we do here is, you can do it manually, or you can use a convol 2D from the scipy.signal, which I'll show a bit later. But what here I've done is, I've just done the loop myself. So from the width and the height, and I would know that since my kernel is 3 cross 3, my resultant image shape would be 2 pixels less from the width and 2 pixels less from the height. So that is why this is the -2. And what is the operation? You multiply the kernel with this window, and you do a summation of it. Okay, and you will keep it in this new array. So your resultant shape is 93 cross 156. And let's see the image, how the image looks like. Okay, so the effect here is not of an edge detection. The effect that I've got is of a blurred image. Okay, so this kernel has just blurred the image. It has not given me any edges. Now let us see the edge detector. So for edge detector, the industry-wide filter, which is a very famous filter, is the Sobel filter, and it is defined as such. And this Sobel filter you can apply, there are two different Sobel filters, one across the X, one across the Y. So across the X is this filter, across the Y is this filter, and we will apply both these filters. This time we are going to use a convol 2D function from the scipy.signal module. Okay, and what I would like to show you is a colored image edge detection. So the image that I am reading is a colored image. Okay, the image is a hand, and what we would do is we would apply the Sobel filter across the X and across the Y, and for all the three channels, red, green and the blue channel. Alright, so when we do it for all the three channels, you would have to apply this filter. This convol 2D function takes your third parameter here as your channel. You apply it for all the channels, and it takes an attribute called mode, which I've kept as same, that I want my resultant image to be exactly of the same dimension of the source image. Now, when we did ourselves, we didn't keep this dimension same. So what happens is a padding is applied here, okay, with 0 values, and the corner image is also taken into consideration. The corner pixels, they are taken into consideration. So once you apply this convol 2D first across the X, then across the Y, then the Sobel operation says that you have to take a square of the resultant Sx matrix plus the square of the resultant Sy, and you take the square root of it, and that answer you will be saving as in your image as your resultant 3x3 matrix. Okay, and when you do it for all of these, so here you're doing for the complete image in one go, and you're doing it for all the three channels. So finally your resultant matrix will be the same matrix, the same dimension of your resultant of your original image. Let's do this and let's see how this image would look like. Okay, so you got this, right, edges for the hand, for the rectangles, and even for these smaller things, just see how perfectly these edges are detected. Okay, let me just increase the figure size. And you would be able to appreciate the kind of detailed edges this particular Sobel operator is capturing. Okay, just see the detailing here. One thing you need to notice is after you do the convolution operation like this, you have to stack your resultant matrix, okay, across the third axis, axis 2, okay, the R, G and the B channel. This is to stack your resultant matrix across the third axis. Okay, axis 2 is 0, 1 and 2 across the colored channel. Okay, and there are many such edge detectors which are already there, and this is one such. Sobel is the industry-wide use edge detector. Okay, when you do convolution neural networks, you do not have to mention these filters. These filters are detected by the network themselves, but this convolution operation, okay, is an image processing operation which I have shown you two effects. One is of edge detection and the second one is the blurring. But many processing is possible using convolutions. It depends on the mask and the filters that you define. Okay, I hope this helps. Thank you.